Good morning, everyone. Buongiorno. That's also about all my Italian, maybe like Tim's. Sorry. I'm very excited to present to you really recent results from the TIPAX project. And my name is indeed Petra Langebroek, but it's definitely not only my work. We have a lot of early career researchers working in the TIPAX project that did most of the hard work. One of them is here also, Dave Chandler, so please go and find him later as well. But I also like to acknowledge especially Emily, Ronya, Benoit, and also some of the more senior collaborators in TIPAX. So I'm going to talk about ocean-ice interactions and tipping points in Antarctica. But now I mentioned a few times TIPAX, and I think maybe half or maybe more of you don't know what this is, what I'm talking about. So I present the project in just one slide here. So this is a European project. It's probably one of the last Horizon 2020 projects. And it's a relatively small European project, so we only have 5 different partners, from partners in Norway, the UK, Germany, and France. And it's very scientific heavy, so we have lots of time or lots of resources dedicated on really digging into these tipping point processes. So we look at ocean ice sheet interactions and at tipping points in the Southern Ocean and in the Antarctic ice sheet, and also, of course, how they influence each other. We are using ocean models and ice sheet models, and also coupled ocean ice sheet models. But for today, I'm only focusing on the ice sheet tipping point and only focusing on using ice sheet models. If you're interested to know more about the other parts of the project, just go to the website or talk with me later. I'm happy to tell more. So I think for most of us, we are actually studying Antarctica because we find it an intriguing scientific topic, right? To be fair. But for the rest of the world, maybe, indeed, sea level rise is one of the main direct consequences of changes in ice sheet size in Antarctica. So global mean sea level is likely to rise, depending on which climate scenario we are following, to about 0.5 meter to 1 meter by the end of this century. But this is, of course, not just due to Antarctica. We have to remember that global mean sea level rise is actually at the moment mostly due to the thermal expansion of the ocean, also due to the loss of mountain glaciers, the loss of Greenland ice sheet, and then a small component is coming also from Antarctic ice sheet loss. However, what I really, really like about this figure in the IPCC report is that it includes this nice dashed line, which indicates somehow low likelihood, high impact scenario that could happen if any instabilities or thresholds are crossed. And here I would say Antarctica could be a major player. So instabilities and thresholds for Antarctica. So there are different ways you can create an instability or cross a threshold for Antarctic ice sheet. So those can be related to atmosphere ice feedbacks, so changes in the surface mass balance, height elevation, melt feedbacks, albedo feedbacks, solid earth interactions, and also ocean ice interactions. And I will talk about that last part, but I'm very excited for the rest of this meeting to hear also and learn a lot about the other possible ways of getting instabilities in Antarctica. So when we're talking about ocean ice interactions and instabilities, the main mechanism that's often proposed is the marine ice sheet instability. So I thought I should at least show it in one slide, in one schematic. So it basically says that if you have a marine ice sheet laying on an inland sloping, a retrograde slope bed, then it's relatively easy to get an instability, because if you have some thinning of the ice shelf in front due to, for example, warming of the ocean, the ice sheet will retreat, but because then the grounding line reaches deeper elevations, you actually have an enhanced ice flux across the grounding line. So that then would cause additional melting of the ice shelf, additional thinning, and additional ice flux and enhanced ice flux over the grounding line. So this is a self-enhancing mechanism. So I'm going to talk here about ocean-ice interactions, no surprise here, and tipping points. And I'd like to talk about both what we think is going on today, what we modeled or think that might happen in the future, and what we simulated for the past 800,000 years. So what is happening in Antarctica today? So I know this map is already 12 years out, 10 years old, so maybe there are newer versions of this map, but I really like this map to get several points across. First of all, it's nicely showing which areas of the ocean are warmer and which areas of the ocean are colder. So the colder oceans protect in some way the Antarctic ice sheet. It also shows that all the ice shelves are thinning, and obviously the ones that are laying in the warmer parts, they are thinning faster. And then the last thing, it emphasizes also where we have most of the ice mass loss from the grounded ice sheet today. So I do like to point out that even in the cold areas, the cold cavities or the colder regions of the Antarctic, the shelf seas, there are observations that indicate warmer waters also reaching the cold cavities. So like, for example, here close to the Filchner Shelf in 2013, there were observations that indicated much warmer waters also reaching those kind of protected, safe areas. So in TIPOX, we mostly do modeling. To tackle this question, did Antarctica cross tipping point today? We used 3 different ice sheet models: Elmer ice, UA, and PISM. Those are relatively different models. And we all set them up to really represent as closely as possible the present-day Antarctic ice sheet. So the details are not super important here, but it's really important that we start with a really good representation of today. And then we did a lot of perturbation simulations. So basically, for 20 years, we increased the ice shelf melt everywhere on different levels. And then we took away that enhanced ice shelf melt back to the original values and looked for another 20 years and for another 400 years how the ice sheet responded. So both during that perturbation time, but also after that perturbation. So this map is supposed to show you how well these different ice sheet models represent the present-day ice sheet, but obviously on this scale you can't really see it. Maybe that's a good sign, but it basically shows that Elmer ice, UA, and PISM are really well initialized to show the present-day situation. And this is a zoom of the West Antarctic part. And now I'm going to show you just one example of a cross-section through a shelf. I take Pine Island here as an example. But if you're interested to see how it works for other parts of Antarctica, just go and look in the paper. It was published last week in the Cryosphere, very exciting. So it's really new results. So on top here now in the middle, you see a cross-section of Pine Island Glacier. So again, that's here. So it shows the cross-section of the shelf, but also of a part of the grounded ice behind. And this is then the simulation for Elmer ice. So we start with the initial state that's indicated with the dot lines here, and it's actually below the colored line here. So with an ice shelf and a grounded part. Then during that perturbation, or at the end of the perturbation, so after the 20 years, the ice shelf retreated, thinned and retreated, and also the ice flux across the grounding line really increased. You can't see that in this figure, but that happened as well. Now for UA and PISM, it's a really similar story. Oh, I forgot to say, so after the perturbation ceased, then so we run the simulation forward, and the ice shelf starts to grow again. grows back to more or less its original location, and also the ice flux decreases. So this is similar for UA and for PISM as well. Even though all these ice sheet models are tuned very closely to the present day state, there are slight differences. So you can see that the grounding line is in slightly different locations. And the dot here shows where the observational grounding line is. So there are some small differences, but the behavior of the ice sheet is everywhere exactly the same. So all the 3 ice sheet models, and also the 3 different perturbation simulations all over really suggest that all the same. Basically, that the present day Antarctic ice sheet did not cross this instability, this tipping point yet, according to our models. This doesn't mean that the Antarctic ice sheet is not losing mass. So it can follow, it is losing mass in West Antarctica, so it is following climate change, but it didn't cross a self-enhanced mechanism, this tipping point mechanism, just yet. So of course then we wondered, when will it cross this tipping point? So we used one of the ice sheet models, PISM, because that one can run for really long time scales, to continue forward in time. So we just continued with the present day forcing, nothing dramatic, no high emission scenario, just present day forcing, just to see what happens then. And for these model simulations, there are, of course, a lot of uncertainties in models. So here I show you different ensemble members. So basically, we took into account the different uncertainties of how exactly do you calculate the ice shelf melt below ice sheets and the sensitivity of the ice sheets to that melt, and also some uncertainties in the basal sliding conditions. So that makes that we have an ensemble of 15 different simulations that we run forward, and all of them, in one way or another, over this time scale, they lose about 3 meters in sea level equivalent ice volume. The map shows where the simulations agree that the ice has been lost. So the more red the color, the more model simulations say that that's where the ice is lost. Again, this doesn't really answer the question of when we cross the tipping point, because it just shows that at some point we are committed to losing 3 meters of sea level equivalent ice volume. So then we did also a lot of simulations reverting this climate forcing, the present day climate forcing, back to historical forcing. So after 300 years, after 500 years, after 10,000 years, to see exactly when these model simulations are not, when they're showing irreversible retreat. And the point of this is that this is very model dependent. So in these simulations, in these 15 scenarios, so to say, there is no simulation where the ice is irreversibly retreating after 300 years. So basically, we can run forward with the present day climate for 300 years in this model, and then we could still go back to our present day ice sheet if we decrease the climate forcing. However, after about 300 to 500 years, 3 of the 15 simulations, they show that we have crossed tipping points and the retreat is irreversible. And on the slightly longer time scales, so the one that I showed earlier, so after 10,000 years, only then we go back to colder climates, then basically all of the different simulations, they show an irreversible retreat. And then this figure shows, again, where this irreversible retreat would be, or how many of these ensemble members show this. So, of course, it's not very realistic to just continue with present-day climate change, but we thought this would be interesting to show and to put some timescales on. Also, quite clear from all the model simulations is that these timescales take time, or these changes take time. So, collapse takes time. It will in the order of maybe thousands of years. Of course, again, if you increase the climate more, so if you go to warmer scenarios, this might be reduced to smaller timescales. Okay, for the last 10 minutes or so, I'm going to talk about the past 800,000 years. For these kind of timescales, we have other issues, I would say. It's really tricky to decide how you're going to force your ice sheet model. In order to run an ice sheet model, you need to know something about the surface mass balance. So we base that mostly on ice core records. We need to know something about the ocean temperatures. And this is a really tricky one because luckily people like Gisela and colleagues, they are getting more and more data for us, but still it is pretty sparse on these long time scales to have temperatures from the ocean, especially a little bit below surface. That is quite tricky. We also do need to know something about the global mean sea level because of other changes in the ocean, either circulation or other ice sheets or mountain glaciers melt or so. So we have really an issue with all these different, getting the information for the forcing right. So we know there are a lot of uncertainties for that. So Dave and me, we have been trying to combine different records. So maybe one paper that could be interesting for this community is that we created the synthesis for sea surface temperatures over the last glacial and interglacial cycle for the Southern Ocean. We're trying to do something similar for deeper ocean temperatures, but it's really tricky. So if you have any great records, Dave is standing there in the back. Now I see you, Dave. Go and talk with Dave or with me because we're really happy to get more information about all these temperatures over those timescales. For the rest of this talk, I'm not going to deal with any of these uncertainties. I'm sorry if you're disappointed, but I prefer to show you nice modeling graphs. And to confuse you, the paleo community, time is going from left to right. So we're here in the present, and this is the past. So this shows our main. We're really happy with this simulation. Our best simulation, I would say, for simulated Antarctic ice volume changes over the last 800,000 years. So in the earlier part of our simulation, we always find an Antarctic ice sheet that is changing, it's variable, but it's always larger than today. While in the later part of the simulation, we see these really nice glacial interglacial cycles with a relatively rapid collapse of the West Antarctic ice sheet and then a slower recovery. So MIS 11, 9, and 5 are behaving really nicely. And then there is one what we call like the field interglacial. So ice started to retreat, but it didn't really continue. And then it went back to not collapsing the West Antarctic ice sheet. So this is maybe, I find it a very fascinating graph, but it doesn't say anything about tipping points, because is the ice sheet just responding slowly to the climate forcing, just following the climate forcing, maybe with some larger response time because it's a heavy mass of ice, or are we really seeing hysteresis behavior and tipping points being crossed? We don't see that from this graph. So hysteresis, to put it quite simply and schematically, you basically compare the climate forcing on the horizontal to ice volume or ice sheet size or area, whatever you want to take. That's an indication of the ice sheet shape. And then, so if we would start with, if we have a large glacial ice sheet and the climate is warming, then it's following kind of this curve where at some point when the climate is too warm, there is a deglaciation threshold where the ice sheet collapses, it becomes unstable, and it's only stable again when it's relatively small, like in an interglacial size. So if we start here in this corner with a small interglacial ice sheet, and we start to cool the climate, also it will take some time before it crosses a glaciation threshold, and it goes back to the large glacial size. So what is happening? Is it a linear response or is there a hysteresis behavior? So in order to test that, Dave did about 90 to 100 equilibrium simulations. So basically, from the black line that we had first, from the reference simulation, the transient simulation, at 90 points in time, we froze the conditions, we continued running the simulation with exactly the same climate forcing of that time. So not changing the climate forcing, but just keeping it constant for 50,000 years. So in that way, we can see where the ice sheet would have liked to be if it was not changed by some climate forcing. So hopefully you can see from all these spaghetti plots that there is a tendency to be above the present-day ice sheet size or largely below the present-day ice sheet size. It's really difficult to find, well, in our simulations, we don't really find a stable present-day Antarctic ice sheet. So to show one of these simulations for the last interglacial, one of these simulations, we're coming out of a glacial state, and then we're warming the ocean by about 1 degree. At some point, this simulation starts with an ice sheet that looks very similar to today, but then if we run it forward for this 50,000 years, in the end, we lose large part here of West Antarctica. So now we're going to dig into this curve a little bit more and look at this kind of hysteresis behavior. So in the first part of the record of the simulation, like I said, the Antarctic ice sheet is always large and the ocean forcing is always relatively cold. So we don't cross any tipping point in this part of time. While in the later parts, so MIS 11 and 9 and 5E, we do really find this hysteresis behavior when we plot it on a hysteresis graph. So we have, I should say here, we have temperature on the horizontal and the ice volume or ice area, I think it is, on the vertical. In the background, these lines in the background is the transient simulation. And all the dots on all the colored dots on here is the end state of these equilibrium simulations. So combining all of that together, we do see this nice hysteresis behavior with a threshold here, a deglaciation threshold, and a glaciation threshold a bit later. Important to notice that it means also that there are two states possible, two stable states, when ocean temperatures are slightly colder than today. So depending if you come from a glacial state or if you come from an interglacial state, you could have a larger ice sheet or a smaller ice sheet. And then there is this intriguing MIS 7 in between. I think we really should study MIS 7 more. I think it's a really interesting period. Because here, the transient simulation did not cross this kind of tipping point where the West Antarctic ice sheet collapsed. So it might have crossed it slightly in the transient simulation, but not for enough time to allow a full collapse of the Antarctic ice sheet. So this is kind of like an overshoot, or you can think about borrowed time or something like that. So the equilibrium simulation show that the ice sheet should have collapsed, while the transient simulation, transient climate, because of climate change, didn't have enough time to actually let the ice sheet collapse. This could be a similar situation as what we are in today. So keep in mind this is a model and this is not really the truth. But today, if we continue with today's climate, also this simulation shows that we would lose part of the West Antarctic ice sheet. So I really hope we can encourage the whole world to somehow reduce our climate forcings, our greenhouse gases, so that instead of following this equilibrium line, that we go like up again, or maybe stay constant. So don't go into a glacial. We don't want that neither. Okay. So over the last 800,000 years, we see all these different behaviors of hysteresis. We see different stable states, we see this overshoot behavior, and we see real hysteresis. Okay, that already brings me to my conclusions. So from these model simulations, I stress these are model simulations, we think that the West Antarctic, or that the Antarctic ice sheet in general has not crossed this large a messy kind of tipping point yet. But if we don't do anything and we continue to emit greenhouse gases, then very likely we will cross that tipping point in the future. The timescales might be sort of long for policymakers, though. In the past 800,000 years, we've seen periods where Antarctic ice sheet was larger or similar to today and where there was no tipping point crossed. And we've seen periods where we have a relatively fast collapse of the West Antarctic ice sheet and a slow recovery. We also find this MIS7, this failed or borrowed time interglacial. And to point out that tipping points were crossed during several of these deglaciations. Tipping points were crossed during several of these deglaciations. And I also wanted to point out that all the glacial cycles are not the same, but they do show somehow consistent behavior. Yes. So thank you for listening. And if you want to know more, talk to me or Dave or visit our website. Thanks a lot.
Okay, questions? Yeah, Kat.
Thank you very much, and it's a very impressive work, and I really appreciated it. When you cross a tipping point, the models don't take the same time to arrive to the tipping point, but did you check whether the geometry was the same for the tipping point?
Right. We should maybe check that. So basically, you're asking to know exactly where the tipping point is.
In geometry.
Yeah, in the geometry. I would assume that it's relatively similar for the models because there are certain points where the ice sheet likes to stabilize.
Yeah, in my model it is the case, but it's also a very interesting point in predicting what is the geometry where it's gone for a long time.
Yeah, so the tricky part of the models is that, of course, every model has slightly different bedrock topography, even though you try to have it as closely as possible through the observed values. Sometimes we don't know really the observation, we don't really have the observations, and the models have all slightly different resolutions. So the first two models, Elmer Ice and UA, they have a variable resolution, so they have really high resolution around the grounding line, but still it's like in the order of kilometer or so, while PISM has a lower resolution, it's 8 kilometers. So we cannot resolve the grounding line exactly, or the topography exactly the same for all the models. Yeah, but the regions will be the same. I'm not sure if we can say exactly this mountain, this sea mountain is the cause, or
Yeah, thank you.
Okay, I have the mic, so I can ask a question. Your results from the PISM model in the very beginning, maybe you can in the meantime try to find the slide, showed that the grounding line was, I would say, about 80 kilometers too much outward compared to the observed record. Yeah, this one. And that will heavily determine everything you say on timescales and stability, because it's now in the model on a very stable point, whereas maybe in reality, it may be on a very unstable point.
Yeah, that's a very good point. So please remember that these are cross-sections, but the models, they are three-dimensional. So maybe at this point, it's not exactly at the right location, but in general, it's more about the buttressing of the whole ice shelf itself. But I agree that if we are on really stable points to start with, it might be more tricky to do this kind of analysis. However, the ice shelf melting was performed quite dramatically. So all of the ice sheets, I think in all of the locations actually, they did retreat from their stable points. So the main question for us was then, how likely is it that after the perturbation is ceased, how likely is it that it will go back to the original state, or will it continue to further retreat? So of course the timescales issue is maybe not very precise because of exactly where the pinning points are today. But I think the tipping point analysis is very properly done, because we really see that after the perturbation ceased, all of the simulations try to go back to their original state and not remove further inland.
Thank you. Well, I need to keep moving on. I'm afraid we're exactly on time.